Hello, everyone. This is Mrs. Leopold here. Um, I will be teaching you, sorry, Unit 1, Lesson 1, and this is not exactly the way I want to introduce myself, but that's all right. We are here with the beginning of the school year. This is function theory, and lesson 1 is about characteristics of functions. What you'll notice about lesson 1, if you've already kind of flipped through the pages, is it's very heavy on vocabulary, definitions, so lots of just basic knowledge here at the beginning. If it looks familiar to you, then go ahead and try to go through the lesson on your own and look at the answer key and see if you can understand it. If you're not sure, you could fast forward to certain parts and just listen to me for certain parts. Or you could reach out to the substitute or reach out to another Algebra 2 trig teacher, or you can wait until I return and then come ask me some questions. But hopefully with the video today and with the notes answer key and with your peers, you can also ask each other, you'll be able to manage this just fine. So let's jump in. So the very first two vocabulary words are relations and functions. So what is the difference between a relation and a function? So you can see just quite basically a relation is a relationship between any two quantities. And we can show the relationship between these two quantities in many different ways. I think in your notes sheet, we have like a function machine there, which maybe doesn't make a lot of sense, but if you have an input value, it's just a visual representation of inputting some value, which is your x coordinate, and then getting the result, your output value, which is your y coordinate. And then again, x coordinate, y coordinate, what am I talking about? I'm talking about an ordered pair there, right? So then I could write a list of ordered pairs. So if I wrote that list of ordered pairs, these would be an example of a relation. Now, I could also write those values in a table. That would also represent a relation, right? So we have our input value, which would be 0, 1, and -7 if I'm looking at the same example over here. And then my output values would be 1, 3, and 3. Or I might represent this relationship as a graph. So this is my x-axis, my y-axis. So here I have 0, 1. So that's 1 point. I have 1, 3. It's another point. Or I have -7, 3. Excuse me. So those are also 3 different ways I could represent a relation. Now, what is the difference then between a relation and a function? Well, if we're thinking about this as the big picture, we have all these relationships between two quantities are relations, so it's more general. And then more specific relations are called functions. So functions are a subset of relations. And a function, more specifically then, is when we assign exactly one output value, which is our y value, to each input value. So let's think about that again. We assign, or there is a one y value for each x value. So here I have an x value of 0, x value of 1, x value of -7. If it assigns only one output value, that means I should not have my x value repeated. So does my x value repeat up here? And the answer is no. So actually this example from above, that set of ordered pairs or this graph, all 3 of those representations of the same 3 ordered pairs is more specifically a function, right? So we have exactly one y value for each x value. So that means your x values cannot repeat themselves. Now visually, if I were to make a graph, so here's 2 different graphs. Remember x-axis, y-axis. So if I graphed a circle versus graphing a parabola, right? Well, which one of these represents a function and which one is not a function? Well, if I want to have exactly one output for each input, so I go across here, this is my input, if whatever this value is, this is my output. Do I have exactly one output for, let's say this is a 1? No. If I look up here, I have 2 output values. So therefore, a circle does not represent a function. A parabola, on the other hand, if I go across to an x value, it's only going to have one y value assigned to it. So a parabola is a function, and a circle is not a function. Now, there is a very simple visual we can do to test graphs to see if they are functions or not. And we call this the vertical line test, right? So if we draw a vertical line through the graph and it intersects that vertical line at more than one point, then this means that that is not a function. The relationship between those two quantities is not a function. Excuse me. If you have your vertical line test and it only hits the graph at one point throughout the graph, then that is a function and it does allow only one y value for every x value. So there we go, we have a vertical line test to test visually for something if it's a function or not. Now, here are four examples. So please look at these four examples and determine are A, B, C, and D functions, and whether or not they are functions, you need to be able to explain your thinking. So go ahead and pause and try to do these on your own and then check back with me. Okay, so A, yes, that is a function. Y, supposed to explain your thinking. So why is that? Well, if you look at this, this is an equation of a line. It's a linear equation, and lines, linear equations are going to pass the vertical line test because for every input value, there's exactly one output value. If you look at letter B, that was no, it is not a function. Why is it not a function? Well, if I wrote these as ordered pairs, 2 maps to 4, -8 maps to 0, 1 maps to 5, but 1 also maps to 3. So because there's not exactly one output value, then that means we do not have a function because the x repeats itself. Letter C is also not a function because it fails the vertical line test, right? So we have 2 y values for many of the x values. When we went across some x value, we can see it's assigned to 2 y values. And then letter D, yes, that is a function because all of your x values are different. It doesn't matter that our y values repeat themselves. It is still a function if your x coordinate is assigned to a different y value. Okay, so remember my diagram. We said, okay, all relationships between two quantities are relations, and then within that, oops, I should have made this color coordinated. That's okay. So we have our big one is our relations right here, and then we have our functions, our more specific types of relations, and then we have more specific types of functions, which are called one-to-one functions. So what are one-to-one functions? Well, here it is right here. Some relations are functions, some functions are one-to-one functions. What is a one-to-one function? Well, it's when the x and y values do not repeat themselves, right? So we have to have our x value and our y value not repeat themselves. Remember my two original graphs? I did one that was a circle. I did one that was a parabola. Again, my x-axis, my y-axis. Here's my parabola. We said, okay, if it passes the vertical line test, then it's going to be a function. So we knew the circle was not a function, parabola is. But if it's a one-to-one function, then our y values should also not repeat themselves. So in order to be a one-to-one function, it needs to pass not only the vertical line test, but it also needs to pass the horizontal line test. So HLT stands for horizontal line test. So of course the circle already failed, so it's not a function, therefore it can't be one-to-one. But a parabola is a function, but it's not a one-to-one function because it fails the horizontal line test. So an example of a one-to-one function would be a line, right? So that's going to pass the vertical line test and the horizontal line test. Another example might be a cubic function if it looks something like that. Or it could be a trigonometric function. Actually, that's false. That doesn't work, my bad. So ignore that last example. So here's example 2. Go ahead and pause and try to determine which one of these is a function and not a function. Or sorry, classified as a relation as function, and if it's a function, decide if it's one-to-one. Okay, hopefully you see letter A is one-to-one. It's a one-to-one function. Every x value is different and every y value is different. Letter C is a function because the x values are different, but it does repeat a y value. And letter C is neither a function, it's just a relation, and that's because your x value is going to repeat. You're going to have an ordered pair that's 1, 4, and an ordered pair that's 1, negative 5. Okay, moving on to domain and range. Obviously, you're in Algebra 2 Trig. That means you've taken Algebra 1 before, or you've taken some kind of math class where you've been exposed to Algebra 1, which means you have heard the words domain and range, I hope at least. So I'm gonna ask you to pause here and try to go through this on your own, answer questions A through D, and then if you're not sure, you can come back and listen, or you can check your answers with me briefly. So go ahead and pause and try this on your own. All right, check your answers. Letter A, does the graph represent a function? Yes, it does. Why do we know that? Because it passed the vertical line test. Is it one-to-one? Nope. How do we know that? Because it failed the horizontal line test. Would you list the numbers to get a domain? And the answer is no. You would not list the numerical values. That would just be isolated points, right? That would be a finite list, and that is not true. This is continuous through here, so there's an infinite amount of values, so therefore we have to do these inequality signs, or on the next page we will see something other than an inequality sign. We're going to start to do interval notation. So here the leftmost point is 2, the rightmost point is 4, so my domain is between -2 and 4. Here my lowest point is 1, and it goes up to my highest point of 3, which is why then my range is from -1 to 3. I'm including, right, so it's less than or equal to, less than or equal to, and now on the next page we'll find another way to write these instead of using inequality signs. So another way to write our domain and range is using intervals. So we call this interval notation. Specifically, if you haven't seen this before, really what you want to hone in on is the fact that a square bracket is inclusive. So square brackets have those hooks on them. And then if it's a round bracket, then it is exclusive. So those are kind of like our parentheses, right? So square bracket is inclusive and round bracket is exclusive. But you might be thinking, well, when is something going to be inclusive or exclusive? Well, you can see right here in this example. This is an open dot, right? So that means it's exclusive. And this here is a closed dot, so that is inclusive. So open dot means that it's exclusive. So if I'm going to identify my domain, well, it starts all the way to the left at 1 and keeps going, and it looks like it's going to go to 4, but that's not quite correct. So instead of going to 4, it really goes to 3.9999999 forever. And so how do I write that? Well, before you might have written something like this. So it's caught between 1 and 4, includes the 1, but excludes the 4. But now we're going to use our bracket instead. So our hooks on our bracket means it's the same thing as this sign, an inclusive sign, including the 1, and then our round bracket here is excluding the 4. So these two ways of writing your domain, those are both the same. They're equivalent to each other. Now your range, the lowest most value is -1. It is a closed circle here at -1, so it's inclusive. And if I were to travel, it's going all the way up. So it goes down here at -1. The highest point looks like it's 3, but it's not 3 because it's an open circle. So it's really 2.9999, but I can't write 2.999 forever because that number goes on infinitely. So instead, I can write 3 and just put an open bracket there. So it's including the 1 and excluding the 3. So again, these are equivalent ways of writing your range. You can use either one. You will see our answer keys. You'll see us transition to the interval notation. But if you like your inequalities, you can still use those. All right, so try example 4 on your own. I would pause here, list your domain and range. This third example might be a little tricky, but that's okay. We give you a little hint here. See how you do, and then you can unpause and check your work. All right, so number one, did you get excluding -1 to 3 inclusive for the domain, and then the range? It's going from 0 inclusive because of this over here. Hopefully you saw that. It's inclusive on the right-hand side, so that means there is actually, this is 1, 2, 3. So yes, 3, 0 does actually exist. So 0 is part of the range, and then it goes up to 2. And then also, did you see here that it's counting, every 2 blocks is 1 unit. So -1 to 3, and then 0 to 2. For letter B, you should have had -infinity to 5 and 0 to infinity. Now it's inclusive of the 5, inclusive of the 0, but anytime you write infinities, so maybe you didn't know this initially, but right, your domain is going infinitely to the left. So it's starting, we always read from left to right. So it's going from -infinity to 5, stopping here at 5. And the -infinity just indicates that it goes on forever, and it's always exclusive because infinity doesn't stop, so you can't include the infinity at the end. If you look at your domain, your range, you're starting at 0, it's including 0 here, and it's going upward forever and ever and ever upward, so it's going toward positive infinity, so your range never stops, therefore we cannot include infinity, so it's just 0 to infinity. Now this third one, it says whenever you have a break in the domain, so this open circle right here was a break, right? So we need to have this union symbol, which means or. So it's going to go from -infinity, right? So from -infinity to -3, then it's an open circle, so I have to break because I'm excluding the -3, and then it continues to go from 3 until we get to 5. It's a closed circle, so I go from -3 to 5, and I include the 5 because it's a closed circle at the end. You do the same thing with your range, right? It's going infinitely lower, so it's starting down here at -infinity, and it's going to this open circle. Ironically, that is at a -3 again, but it's my y value this time. So I'm excluding that -3, and then I continue to go up until it doesn't go up anymore, which is at +3. It's a closed circle, so it's inclusive, hence the square bracket there on the end. All right, you can practice with 2 more here on your own, and then check with me, or actually I'm going to skip these 2. You can check back and look at the answer key for help if you're not sure. All right, new definition, function notation. Again, if you've exposed yourself to an Algebra 1 class or concepts from Algebra 1, then you have definitely already learned about function notation. That's your f of x notation, right? So your y value equals f of x. So it's saying, we're inputting some x value to get a y value as a result. So if I said, hey, the function is 3x plus 1, and I put f of 3, well, this is saying, okay, if we insert 3 for x, then what are we going to get for our y value? Well, we would put 3 times 3 plus 1, because I'm inserting 3 into x, so 3 times 3 is 9, plus 1 is 10. So in other words, when I input an x value of x, I get a y value of 10 if this were my function, and that represents a point on the function. So now we're going to do this graphically. Here you can see on the right-hand side, we have a graph of g of x. Letter A, it says, is g of x a function? Justify your response. So hopefully you're saying to yourself, okay, if it's a function, then it should pass the vertical line test. It doesn't say one-to-one function, it just says function. So if I were to go through here, that looks like it's not going to pass, but it does because it's open circle, closed circle. So yes, it is a function because it passes the vertical line test. So yes, it is a function because it passes the vertical line test. What is g of 3? Well, 3 is my input value. It's saying when x equals 3, what is my y value? So I'm going to go 1, 2, 3. Here's when x equals 3. I go up. If x equals 3, what is the y value? The y value is 2. Now you can go ahead and pause and try to do the rest of this, or we'll just do it together. So what is g of -1? Well, when my x value is -1, what is my y value? So I go left 1. Well, this is where the circle is closed, so my y value is -1. This is open, so there is no y value there. what is g of 10? I go all the way to the right here at 10, and when I go down 10, the graph stops here. So there is no y value associated with 10. Therefore, I'm going to write DNE. Why am I writing DNE? Because DNE means does not exist. So there is no y value associated with the x coordinate of 10. Therefore, I write DNE does not exist. So now the next section says, okay, well, where is g of x less than 0? So what is g of x representing? G of x is representing y. So in other words, it's saying when does y have values that are less than 0? Well, values that are less than 0 just mean negative. So in other words, it's saying when is y negative? Well, y is negative anytime the graph has values below the x-axis. So this is going to be an interval. So we need to write an interval notation. So all of these y values are below, they're negative, and then all of these y values are negative until we get here. Now, it is not inclusive of 0 here when I look at this over here on the left-hand side. It's when the y values are less than 0, not equal to 0. So I'm only going to do my y values that are less than 0. So therefore, I have to exclude, it goes all the way until it looks like it goes to 2. So from negative infinity to 2, but I'm going to exclude the 2 because at 2, it looks like it's 0, not less than 0. Or I'm going to continue, right? So now these are all positive, so I can ignore that for now. And then I get here, it looks like 7.8 or 7.9. If you put 8, that's okay. So roughly at 8, I'm excluding that, and all the way until we get to 9, my y values are negative. Now I'm including the 9 because exactly at 9 there's a negative y value that exists, but I'm excluding the 8 because at 8 it looks like it equals 0. If you put a 7.8 there, 7.9, that's okay too. Now the next section says when is the y value greater than or equal to 0? Well, you can see here that is from 2 to 8. In between 2 and 8, all these y values are greater than or equal to, so I can include the 2, include the 8, because those are when the y value is exactly 0, and it was inclusive here. All right, if at any point you're having difficulties, you should pause. You can ask the substitute, you can ask your neighbor, a peer in there, or seek me out or another math teacher out, and we'll certainly help, or we have tutors in the library who can help you as well. All right, we're getting close here. More vocabulary, maxima and minima, and then within the maxima and minima, we have absolute maximum, absolute minimum, and we have relative maximum, relative minimum. I'm going to go ahead and have you read through these on your own. They should be pretty self-explanatory. And then this down here is just your little cautionary word. So it says, yes, they are explanatory. And then I just really want to point out to you that it says, generally speaking, what we will not assess. So go ahead and read through all this on your own. I don't think me reading it aloud is necessarily going to help. And then we'll do the next example together. All right, so let's do example 8. Letter A, it says, what is the absolute maximum of this function? So the graph drawn over here to the right is your function. So the absolute maximum is referring to the y value that is the absolute ultimate highest y value in this graph. And hopefully you're just saying to yourself, it's right here. So the ultimate maximum or absolute maximum, is 4. And that is your y value, right? So I just want to then quickly contrast this with letter C. Letter C says, what is the absolute maximum point? Okay, the point is your ordered pair, right? And so we were taking the y value, the absolute maximum is just the y value. And then it says, at what x value does it have an absolute maximum? Well, my x value associated with that is -4. And so what is the absolute maximum point? Well, that's your ordered pair of -4, 4. But if we just say, what is the absolute value? Not absolute value. What is the absolute maximum of the function? You're just giving us a y value. If we ask for an absolute minimum of the function, you're just giving us a y value. Now in this particular graph, what is the absolute minimum of this function? Well, you go to the ultimate lowest point and you go, wait a minute, it's an open circle. And if it's an open circle, that means we do not have an absolute minimum, so therefore it does not exist. Now, what are the relative minimums, and at what x values do the relative minimum occur? Well, we have relative minimums right here. You know, it's when it's changing from decreasing to increasing, so we have a relative minimum at, a relative minimum of 1. We have a relative minimum of 1 here when x is equal to -3. And here's another one because it goes increasing, goes decreasing, back increasing again. So this is another one. So that occurs at when x is equal to 1. There's another relative minimum 1. And actually right here, you could also say this is a relative minimum because values to the right and left of it are also higher than it. So we could also say at 2, there is a relative minimum. Now, this is the example that we will not assess because that's a little tricky sometimes. So they are going to be clear if they're minimums, like these first two examples. This one, it's a little bit tricky, so we will not assess that. Now, what is the relative maximum? So the relative maximum is when it's going, from increasing to decreasing. So right here is a relative maximum. What is that relative maximum? Well, it looks like it's a value of 3. So sorry, here, this was over there. And when does it occur? Well, it occurs when x is equal to -1. Do I have any other relative minimums? No, I don't. That's it. All right, and our last vocabulary is decreasing, increasing, or constant. So we're going to identify intervals on the graph where the function is decreasing, where the function is constant, or where the function is increasing. So let's go ahead and look at this. So decreasing, I always say we're looking from left to right. So decreasing is when you're walking down the hill. Constant is when you're not walking up or down at all. And then increasing is when you're walking up the hill. Again, if you're going from left to right. So here is the more scientific way of describing it. Decreasing is on the interval of the domain when the y values decrease and x values increase. Constant is when y values remain constant when x values increase. And increasing is when the y values increase as the x value increases. So look at this next graph. I would like for you to pause and identify the intervals where in the graph you have constant, where it's decreasing, and where it's increasing. So pause, do it on your own, and then check back with me. All right, so look at the intervals that I have. I've also color coordinated them in the graph. So hopefully you should pay attention to, do you have the U, right? So your union, right, symbol right here, because there were two different parts. Do you have proper exclusive and inclusive? This is inclusive, exclusive, exclusive, inclusive. So do you have those properly done? And do you have the proper numbers? So you want to check on all three of those things. And if you're not sure, then pause and ask someone around you. And finally, this last example, you should be able to take off on your own, put it all together, and then check your answer key in the notes to see how you do. If there's any intervals that are not quite perfect, then you can certainly approximate, like if your x values look like they are halfway in between two different ones, you can just approximate. But otherwise, yeah, do your best and double check. And I hope everything went well. And I'll hopefully see you soon. Bye.